So this is the explanation of example number 25. I forgot to record it in class yesterday, so I'm going to make another video. All right, so in this example, you have a sea lion sliding from rest down a 3-meter long ramp into a pool of water. It tells you the angle of the incline, the coefficient of friction between the sea lion and the ramp, and it wants to know how long it takes for the sea lion to make a splash in the pool. And so this problem doesn't have a lot of numbers in it, so we're going to have to solve it with the equations, with the variables, and then plug in the numbers once we can eliminate some of the variables. So if we start by drawing a picture, it's not a very good picture, but it'll work. Here's my ramp, and my angle is 23 degrees. Okay, here's my sea lion. Everything is a box or a dot, circle, something like that. And we know that the force of gravity is going to act downward, and the normal force is perpendicular to the surface of contact. So here's our force of gravity. And if friction will be acting up the incline because our sea lion is going to slide down the incline. So our acceleration is going down the incline. Hence, friction is the opposite direction. If we break up our gravity component into the perpendicular and parallel components, remember this is a right triangle, this is the same angle, then we can write the equations for the normal force, the frictional force, force of gravity, all of that. So I'm going to switch colors here. So first off, we know that the force of gravity is mass times 10 meters per second squared. This is our perpendicular force, and since it is adjacent to the angle, it's going to be the force of gravity times the cosine of 23 degrees. This is our parallel component, and because it's opposite the angle, it's going to be mg times the sine of 23 degrees. So our normal force is the same as our perpendicular component. So I'm just going to write that there, mg cosine 23 degrees. And we know that our force of friction is equal to the coefficient times the normal force. So we can plug in mg cosine theta, or the angle, right there. And so we can say that the force of friction is equal to the coefficient of friction times mg cosine of 23 degrees. So friction is going to act upward, the parallel component is going to act downward. So our net force, and we're looking at this x-axis here, which remember we kind of tilt that on its side. So this is the x-axis, is going to be equal to the mass times the acceleration. Well, we have the parallel component minus the force of friction. That's going to give us our net force, which will be equal to mass times acceleration. So let's plug in these equations for parallel and for friction. M times g times the sine of 23 degrees minus the coefficient times mg cosine 23 degrees is equal to m times a. Now we weren't given the mass of the sea lion, but if you look, you have mass here, here, and here, and because it's in every part of the equation, we can factor it out, divide, and get rid of it. And so now I can plug in numbers that I know and solve it. So 10 meters per second squared times the sine of 23 degrees minus 0.26 times 10 meters per second squared times the cosine of 23 degrees is equal to a. And so when you solve that, you get an acceleration equal to 1.5 meters per second squared. But that isn't what the problem ultimately wanted you to find. It wanted you to find how long it was going to take him to splash into the pool. So let's go back to the original problem. We know that the sea lion starts from rest, and we know that the ramp is 3 meters long. We know the acceleration, and we're looking for time. So we have to use the delta x equals v initial times t plus 1/2 at squared equation. This is equal to 0, so 3 meters is equal to 1/2 times the acceleration times time squared. And when you solve that for time, you should get 2.0 seconds. So it takes the sea lion 2 seconds to slide down the slide and into the water.